a PhD student at the University of Waterloo, and he's taking advantage of the fact that we have a wide range of halo masses in the go-green sample to look at the role of halo mass in galaxy evolution. Go ahead, Andrew.
Thanks, Michael. How's my audio? How's the video look?
Audio is good, but I think you're showing the wrong slide. We're seeing your
you're showing the presenter view.
Presenter view.
Thanks. Yeah, I can flip that. Probably. Did that change it?
Yeah, that's perfect.
Oh, excellent. All right. I'll just hop right into it. I was going to do a quick reminder of quenching, but I think it's been mentioned so many times now what quenching is. I'll just move straight into two key concepts I wanted to introduce for those of you who don't necessarily work in our neck of the woods of galaxy evolution. So the first being dark matter halos and how a cluster is built up from dark matter halos. And the second key concept I want to introduce is more of a nomenclature thing, but does provide a framework for thinking about it, the problem, which is central versus satellite galaxies. So the first concept I want to introduce is that galaxies reside at the center of a dark matter halo, basically a clump, gravitationally bound clump of dark matter. So galaxies form at the center of these halos as hot gas that is held together by this massive dark matter object. As this hot gas cools to the center, it can then feed star formation and form a galaxy that we can see with our telescopes. So these dark matter halos with galaxies in the centers of them merge together over time as the universe evolves. And so you get this buildup, almost like a tree, as you have these successive merging events. And so you get something, say, at go-green redshifts, which I'm looking at, like a galaxy group, which has a number of galaxies in it. There's some large dark matter halo, and then there's subhalos within it that may be, for example, individual galaxies. So this accretion history can matter and influence the quenching of galaxies within the halos and subhalos throughout cosmic time. So here's that plot again that we've seen a few times of cluster mass versus look back time, illustrating our go-green sample with the green points and G-class in the red. And down here we get into the groups regime, which is, in my notation, anything less than 10 to the 14 in solar masses. And so the region I'm probing in this work that I'm going to do a broad overview of is basically redshifts 1 to 1.5, and it's about 20 groups, not just our go-green spectroscopic groups, but additional groups in the Cosmos and SXDF survey regions. And any halo masses are estimated using X-ray fluxes, although we also do velocity dispersions as a check. Okay, so there's the second key concept I mentioned that I wanted to introduce, which is central or satellite galaxies. So in this left plot here, we have a rough illustration of a galaxy, which, if it's a central, means it's at the center of its dark matter halo. And so gas will accrete onto that halo from the surrounding regions in some kind of cosmological inflow. So that adds to the hot gas reservoir of this central galaxy, the extended halo of that galaxy. And so this hot gas can then cool onto the center, and that can fuel star formation. The star formation, as well as the death of stars and supernovae, as well as the cooling gas accreting onto the central black hole, supermassive black hole. These can all provide outflows, which then reheat the gas reservoir and slow down this cooling and star formation process. And so an isolated galaxy can continue doing this, especially if it's a lower mass galaxy, for quite a long time. Basically the entire history of the universe if it's a lower mass galaxy. But if this galaxy is to fall into a larger dark matter halo, such as a galaxy group or galaxy cluster, it's no longer the dominant gravitational potential. So there's this very large gravitational potential of the cluster, and as cosmological material inflows into the cluster, it doesn't necessarily fall into the galaxy. So the galaxy loses its source of fresh gas, and so it will prematurely end its era of star formation and be quenched earlier than it would if it were a central galaxy. So my work aims to constrain or understand how quenching processes in galaxies depend on their group or cluster halo mass at redshifts 1 to 1.5. I do this by making use of go-green cluster measurements as well as the group measurements, which I've done explicitly in my work. And this work fits into the core go-green science goals, namely environmental quenching of low-mass galaxies is relevant, and better understanding hierarchical assembly of baryons. A unique feature of go-green, so the unique features of go-green that were mentioned in an earlier talk, namely the wide range of halo masses and the depth of observations for low-mass galaxies, are both extremely important to allow this to be even done. So the simple method I've been using to measure, I guess, the statistical properties of groups is a background subtraction routine. And I've been doing this for, I guess, three catalogs: UltraVista DR1, DR3, which is a deeper catalog, but only probes certain stripes within the cosmos field, and then the Splash SXDF survey. So this background subtraction method is quite simple in essence. The number of galaxies with a given property is equal to the number of galaxies in some circular aperture minus the number of galaxies in that field survey region. And that subtracted quantity is weighted by the relative areas of the circular aperture to the field, area of the field. And so I sum over all groups, average all three field regions, and then I can calculate things like stellar mass functions. I guess I'll note that quiescent or star forming color cuts are done using the U minus V versus V minus J color cuts, similar to others in the go-green collaboration. And that this background subtraction routine is done for groups within some delta Z, some redshift cut, depending on the quality of the photometric redshifts and how precise they are. For a given stellar mass bin, error bars are simply Poisson, and there's other details, of course, but these are the salient points. So I'll present some results. So this is, I guess, a simplified stellar mass function showing derived from simplified stellar mass functions. So this is the quench fraction versus stellar mass for the field, for the groups that I'm looking at, and then for the go-green intermediate and high mass clusters. So what's really clear here is the stellar mass trend, which is well known, that quenched fraction, the fraction of galaxies that are quenched in a given stellar mass increase with increasing stellar mass. But also visible here is that the groups have an enhanced quenched fraction relative to the field. And then yet again, the clusters, go-green clusters, have an enhanced quench fraction relative to the groups. There's not necessarily a clear, simple monotonic trend here, but there's this overall trend of, it seems that higher stellar mass or higher halo mass environments have higher quench fractions. So I can also plot this as a quench fraction excess plot, like mentioned before. So I guess the intuitive picture I use for quench fraction excess is if you took some blue or some star forming fraction of galaxies and they fell into a cluster, and instantaneously quenched, what fraction of them would be quenched as they fall from the field into the cluster? And so this quench fraction excess is similar to the previous plot, but basically just in simplified way shows that If we're above 0, there's an enhanced quenching of galaxies in groups, and then that enhanced quenching in clusters. I'll bring this back up again when comparing to some literature in 2 slides. So I guess putting things in some context in terms of redshift would be helpful. So this is that plot that Remco showed earlier today, showing quench fraction excess versus redshift. So I've added a few points onto this Nante al. 2016 plot, but basically there's an overall trend for groups, at least shown on this plot, where the quench fraction excess seems to decrease with increasing redshift. I've plotted on some of my own derived values here. The work I'm presenting is namely this point. So here's a probably more useful breakdown, which shows some works, different redshift bins. This is low redshift, intermediate redshift, and higher go-green redshifts. This is that plot I've shown you. And then each plot's quench fraction excess versus stellar mass. So there's no clear redshift evolution for a given halo mass bin. But what is evident, at least to me, is that if you look at a given halo mass, the quench fraction excess increases with increasing halo mass, at least overall. But the overall trend is obviously not super clear from these plots. So I'll end with this slide with, I guess, a few thoughts about what does this mean. So we commonly observe environmental related processes in most massive clusters. And when people do quenching toy models, they seem to indicate long quenching timescales in the literature at low redshifts. In Go Green, we're seeing a very high excess of quenching observed even in early modest structures such as groups at these Go Green redshifts, which indicate that quenching timescales are actually shorter in the early universe. Quenching or galaxy formation mechanisms in the early universe, that means, or clearly need further study. As well, accretion histories of groups and clusters are different, but also theoretically well understood. And there's different ways of approaching how to look at an accretion history. But what I'm doing right now, and will be included in the paper, is we're going to combine our observational quenching constraints with toy accretion models for different halo masses and different accretion models to constrain timescales associated with quenching, and then compare to the low redshift universe and see what insights that provides. Thanks.
Great, thank you, Andrew.